Let's say I have two species of animals in sizes A of t and B of t. If these population sizes grew according to the equations dA dt equals mu times A and dB dt equals lambda times B, with growth rate parameters mu and lambda, which are positive numbers, what can we say about the growth of these two populations? These two equations are equations for exponential growth. In this case, the growth never slows down, and the populations don't influence each other. In the exponential growth model, the population sizes will grow unbounded. To make the growth more realistic, we could introduce carrying capacities. Let's call them K sub A for population A, and K sub B for population B. And these carrying capacities reduce the growth rates as the population sizes get large. We can use the logistic growth model to model the population growth with the carrying capacity. We multiply the equation for A by 1 minus A over K sub A, and the equation for B by 1 minus B over K sub B. So in this case, the growth will slow down as the population sizes reach the carrying capacities. The equations are uncoupled, meaning the equation for A does not depend on B, and the equation for B does not depend on A. So again, we have no influence between A and B. The population sizes of species A and B grow independently according to their own equations. Let's make one slight change. Let's make the carrying capacity terms depend on each other. For the equation for A, rather than the growth rate being slowed down by the factor 1 minus A over K sub A, it will now be slowed down by the factor 1 minus A plus B over K sub A. This means that as the population size B increases, it will slow down the growth rate of population A. And vice versa, since the equation for B is multiplied by 1 minus A plus B over K sub B, as the population size A increases, it will slow down the growth rate of population B. It's as though B uses up some of the carrying capacity for A, and A uses up some of the carrying capacity for B. This means that the equations are coupled, meaning the equations depend on each other. In this model, the two species slow down each other's growth by using up the carrying capacity. In this way, the species are competing for resources. We have formulated a model for competition. To further examine the behavior of our model of competition, let's put in some specific values for the parameters. For the growth rates, let's let mu equal 0.2 and lambda equals 0.5. So in this competition, who seems to have the advantage? As far as the growth rates go, B has the advantage with its faster growth rate. This should help it outcompete A. For the carrying capacities, let's set K sub A equal to 1000 and K sub B equal 500. Now who looks like they're winning? As far as carrying capacities go, A has the advantage. Population A can get larger than population B. Let's write down the equation with these values. So what's going to happen with this competition? Will B win out with its faster growth rate? Will it be able to grow so fast that A won't stand a chance? Or will A win out with its larger carrying capacity? Since it seems A can get larger than B, maybe that will be enough so that it can stifle the competition. After all, what happens if A gets larger than 500, the carrying capacity for B? Then A is eaten up more than the total of B's carrying capacity. So it seems it might push B to 0 in that case. Or maybe there will be no winners. Maybe neither population will win or lose, and we'll just have some peaceful coexistence between the two populations. Let's take a look what happens by using a simulation. We'll let the computer approximate a solution to this system of equations and explore what happens with this set of parameters. This applet demonstrates the behavior of our competition model. Since this applet uses the variables x and y, we use x for A and y for B. And we have entered our differential equations into these boxes at the left. In terms of x and y, dx dt is 0.2 times x times the quantity 1 minus x plus y over 1,000. And dy dt is 0.5 times y times the quantity 1 minus x plus y over 500. Currently, the initial conditions of both species are set at 0. When we plot t on the horizontal axis and x, or A, on the vertical axis above, and y, or B, on the vertical axis in the bottom plot, both A and B are 0 for all time, as shown by the flat blue line at 0 for A and the flat green line at 0 for B. If we increase the initial conditions for A, we can see that the population for A starts growing. It initially grows exponentially, corresponding to its low density growth rate of 0.2. If we increase the time from 20, let's say to 100, we can see that the population size for A saturates at 1,000, because 1,000 is the carrying capacity for A. On the other hand, if we reduce the initial conditions for A back to 0 and set the initial conditions for B to be positive, then we see that B grows faster because it has a low density growth rate of 0.5, but it saturates to a lower value of 500 because its carrying capacity is only 500. What will happen if we set the initial conditions of both A and B to non-zero values? Here we see that B initially looks like it's winning because it's growing faster than A. However, since B's carrying capacity is 500, its growth rate slows down faster than that of A. And since B can never grow any larger than 500, it can never eat more than half the carrying capacity of A. So A steadily gets larger and eventually eats all the carrying capacity of B, bringing B all the way back down to 0. So it seems like the population with the larger carrying capacity wins. Is this true in general for all initial conditions and all values of the parameters? You can explore this question with the applet by changing the initial conditions or changing the parameters in the equations. If you want to come up with a definitive answer, so you can understand what will happen for any initial conditions or parameters, then you have to do some analysis of the equations and see what you can determine mathematically. But for now, you can play around with this applet and see what conclusions you can make. You can also explore the behavior of this model with the second applet on this page. This applet shows not only the plots versus time of both population A, or X, and population B, or Y. It also plots the state variables x, y, or a, b, in the phase plane, where the horizontal axis is the population size of the first species, population A, or X, and the vertical axis is the population size of the second species, population Y, or B. Here we can see that initially the second population, B, grows faster, but eventually the first population wins out, sending the second population to 0 as the size of the first population heads to 1,000. In this applet, you can vary the initial conditions by changing the value of x separately, or the value of y separately, or by dragging the point in the phase plane, you can change the initial conditions of both populations simultaneously. Especially in the phase plane, you can visualize how the population sizes flow with time. You can see how when both population sizes are small, the flow favors population B, but when the population sizes are larger, the flow favors population A. By playing with this applet, you can familiarize yourself with the relationship between these two different ways of displaying the evolution, plotting the solutions versus time on the left, and plotting the solution in the phase plane on the right. The phase plane is an important tool. We'll use it extensively to understand the behavior of two-dimensional autonomous systems of differential equations. It will help you understand our analysis of these differential equations if you can become comfortable with the phase plane representation.